Welcome to a new test and teardown video. This time it's another Hewlett Packard. This time it's a 5-digit Nixie counter called 3734A. I think it should handle about 5 megahertz. So I'm a little bit curious to see if that is really right. I don't know if you can see these different marks I got here. And here, and here, and I also got some 2 stickers on the side. I mean, why do people put stickers all over their instruments? It's driving me absolutely nuts. So please tell all your friends not to put stickers on instruments, at least not the front panel, please. Yeah, I don't know if this thing works or not, but I'm a little bit excited about another Hewlett Packard, because this one is my number 62 Hewlett Packard instrument. Yeah, 62. Who's counting? This one is without the data recorder interface, but of course it got start-stop external inputs, so it can of course do stuff like that. You can reset disable or normal, internal oscillator or external. And we've got 2 fuses and obviously this fancy smancy good old connector. And it should be from about 1966. I think there is a trick to look this up on the serial number. Maybe I will do that later. Of course I got these power cables here, so I should be able to power it up and see if it works. I think we should do that. So here goes, all or nothing. Yeah, I think this is the power. Yeah, there's the power on-off switch. I wanted to test the power switch as well. So I will turn on my mains and I see 0.0 watts. So that is perfectly fine. And we got light. So this will be the hold time. See, there's a reset problem here, right? Ah, this is the sensitivity. And the check. Well, why isn't it resetting? So this is the frequency. Okay, so it's full of all sorts of problems. Oh, that is a little bit interesting. This lamp here, I thought this was the... Oh, it is working while we got hanging digits. Or what? See? We got something that is... And, yeah. Let me try and input something and see what happens. So, here is one... Let's put in 1.234... 1.234 kilohertz, right? So at least we see something going on here. So this is sensitivity. I think I can see a... I don't see anything. What is going on here? It is a dead as a... Anyway, time interval external. Maybe there's a time base issue or something. Maybe I just put the time base in the wrong... Oh, oi. So it's count. So now we got time base, right? So this is time. See? So something is working and the Nixie's interesting time interval. Ah, see, here is the start stop. So this enables some sort of, and then this is external. Okay. Well, I need to open and have a little look. So this is the first little peekity peek inside, and it is very, very dirty. So that is something I will fix. First of all, it is nasty. All over the place. Look at all the dirt. But I think a little bit of compressed air and a little brush is going to make it nice and shiny. And then I can probably carry on with my little clean and fix and maybe find the problem. That is one big surprise. And now I'm opening this unit all over the place. And what the heck am I finding here? I just said a lot of really nasty words. I will refrain from repeating, but look at that. What could have happened here? I used this plug for power entry, and what is that? What kind of a mega muppet would leave something like this inside an instrument? What a mega muppet. I could have blown up everything down here, man. This I am super pissed about, to be honest. But I can also be a little bit angry at myself for not performing a deep going inspection before I power up stuff. I need to remember to tell myself, let's always do the good old deep going visual inspections, because you never know what you find. But it looked so nice. What the heck, man? But also I see a lot of rust all over that. So it was left outside in the rain or something like that. Look at that, rusty. And here, this explains how some of the features, they're just gone. So what we're gonna do is we're gonna clean up and we're gonna remove all the corrosion and stuff like that all over the place, and maybe that is all it takes to get it up and running. I'm probably gonna find some more funky things when I look more in detail here. Probably some leaked capacitors or something like that down there. Well, what a day, what a start. So I'm going around cleaning up here and figuring out what is going on. I really cannot find any free service manuals, schematics, anything online that is easy to access. Sucks. So that will be the circuit board that was located up here, and it definitely looks like this trimmer here could need a replacement. So it's a 1K trimmer. So that one I need to definitely figure out how to fix. So this is the counter section here. See, slide out a decayed divider assy. So this one was located the other way around, right? And there's a module missing, but I think this is the optional 10-second time base. So I think this is the time-based system, and that will be the optional. And again, I cannot tell you exactly because I don't have the service manual, but it's nice and easy to measure this while it's out like this, right? Yeah, I tried to clean a little bit here, but look at how nasty it is all over the place. That could definitely be why it is not working. Also, try and look at the, oh yeah, here it is. Between those pins, you see some corrosion between those two pins, right? That could also be another explanation. So I'll just take out one of the circuit boards at a time, do a little cleanup and put them in again, and then see if there's any luck. This can't be good. And it's also in the contact. Ooh, nasty. How do I clean that? Let's look a little bit deeper onto one of the counter or dividers here. So I really tried to clean the corrosion we had between those two connectors. So here it's nice and beautiful now. And the back side is also, yeah, sort of nice and clean. But if you look under some of the resistors, like here, can you see what I'm talking about? And we got some nasty corrosion from some of the pins of the resistors, and it goes under the resistors to some of the tracks under the resistors, causing all sorts of, yeah, I don't know if this is causing leak or whatever it is. See, here is a 47 kilo resistor. Here we zoom in on this resistor. You can see the funny corrosion going under it. I don't know, how do I clean this? Oh no, and that one here. Can you see this one in the middle? Oi. Not so easy. So what do you think about this circuit board now? This is exactly the same circuit board. Ooh, magic. Yeah. It is definitely clean as new. Oi. Maybe I should show you what I did to this board, but oh, it is brand new and nice and clean. So first is what I do is just take burning hot water and make the circuit board as warm as the water. Don't you worry, the circuit board can easily handle all this heat. And then I take washing soap and just splatter a lot on it, and then it's just do the rub everything here and wash it from all angles under all the resistors and capacitors, and try and come in. Of course, you don't want to rub off all the components. See, here is a capacitor I need to be a little bit careful about, but this is really how I do it, and I try to change the angle here so I get all the way under all the resistors and all that kind of stuff, and of course also a little bit on the back. And then of course I flush it in burning hot water, and then I clean this up, remove the water by drying and give it a little bit of compressed air, and it is going to be nice and fine. And when it is really nice and warm and you compress air this and just have it in your hands for 2 seconds, then it's going to be completely nice and dry and nice and clean. So the board, this is called the A1, and that was the one with the absolutely nasty corroded trimmer. And of course I tested this one, and when you dial around with this one, you get anything in the between everything, right? So it's not working in any way. But I actually measured the resistance where it was in the circuit, and then I put in a new one and adjusted it to exactly the same value as the previous one, because I think I was lucky there was actually a connection when it was there. So I don't know, this is just my starting point at least. So now this board is clean, and yeah, I'm also continuing to clean all these boards here, and it goes really well. I'm having a lot of fun with this instrument. Damn, I hope I can figure this out. But I actually got a lot of stuff up and running and working so far. Now I'm just taking out all of the boards and doing a deep clean of everything. We'll also find some really simple boards in here as well. So that's just an unregulated power supply with all those rectifiers and stuff like that. And then it goes to all the capacitors down here. And then it goes back again. And then there is one of the supplies is actually regulated, I believe that one. And then we got a transistor sitting somewhere down here, and that is doing some of the logic stuff for the transistors. Neatly, all the connectors, they have this power and then this 65G, and then you will find written on the board 65G, and then you know where to plug in your boards when you have not done such a mess with all the boards and stuff all over the place, and it's nice to know how to put everything back together. Also, the front glass consists of two parts. See, the tinted glass and then a transparent glass. And I want to take both of them out. I believe that when I've removed this part and removed all the readout modules, I will be able to pull these glasses up so I can do a proper clean. It looks like it's more or less nice and clean now because I cleaned them on the outer sides, right? But I wanted to show you some of the different modules. So up here we got an oscillator board with this crystal and the frequency adjustment right there. It is 100 kilohertz. And this oscillator here looks fairly simple, but I think it's quite funny because we got this part here. It's called ABCD, containing some super secret stuff. But I do not have the schematic, so I cannot tell you exactly what it is. It's maybe a little LDR and an LED. It can also be another sort of optical or some stuff like that. I just don't understand exactly why they're using this part for the oscillator board. So anyway, I'll put that back up here. We got the display board and the gate board. So let's see which one is this. So it's called 65E and this is the D. Okay, so this is the gate board. See, I did a nice job with the cleaning. So why is it on the gate board we got the two neon bulbs? That's a little bit interesting. And that transistor here, wow, look at that. That is one oldie. And also it looks like it has been replaced. It's a 2N1, 69 or something like that. Yeah, 69A. Well, that is one old fantastic transistor, huh? I don't know what the heck that board is doing other than gating. But we still have one little board left to look at. And that should be the 65E up there. And this is the display. So what the heck is this doing? I think it handles the reset of the display, counting or resetting. I don't know exactly what it's doing, but it must be something like that, right? So the display boards, they are a little bit different. The two modules to the right, they are different, and that's because they're using a much higher bias current and faster transistors. So the whole coupling here is running at super speed. And that is because this unit should be able to count to 5 or handle 5 megahertz. That is just not the case at the moment. It handles only 300 kilohertz. So I think something is wrong. And my first approach to figuring out what is the problem, that is to try and swap the two fast modules. And that is why I have marked them, so I know this one is not the one to the right. The one to the right is this one. And then I will swap these two because they are completely identical. And then I will see if I still got exactly the same count speed problem. So at least that is my first approach, because then I know it is the count modules or not the gating or enabling, storing or anything like that. The other three modules to the left, they are identical as well. And I also keep them in the same order here. And they are the famous modules you have seen a million times before in all those counters. I have done tons of videos about these modules, But this one here is the one in the middle, and that one is causing a little bit of funny counts sometimes, and also it's doing some little extra flippity flips with the display here. So why is it doing that? I got a few ideas, and I wanted to show you the two modules on the back side. Look at that. Can you see what's going on here? Let's compare it to the one that is working. Ooh. So there's a solder blob here in this location. See? This can't be true. This can't be right. So I will try and remove this little... Yeah. And then I will see if it works. I'll of course clean the tubes and all that. So those are the top lid 1022s. I didn't clean the tube yet, but I cleaned the boards and the contacts a little bit. See, this one I didn't clean so well. But this one works super duper nice. So yeah, I think it's time to assemble and then do a little bit of testing. So I think I want to show you a little bit about my problems. And you can see it has something to do with the reset circuit. See, I'm inputting 1, 2, 3, 4, 5 hertz. So that is 12 kilohertz, just to let you know what's going on here, right? So just to make this a little bit easier. Now let's gate a lot faster and see if I play with the hold time and put it a little bit down here for you. See what's happening? You can see it's not doing a proper reset, but when I do it fast, see, there's no reset whatsoever. It just goes, see, on and on and on and on. But if I go slower and slower and slower, yep, here we go, and then it's stable. So there is some timing in the reset stuff that is not working correctly. I can of course hit reset here. So manual reset works, but it's the timing logic that is doing the transfer and then the count. Because we got the two sets of counter. We got count and transfer, right? Because this one is counting in the back and then it's transferring. And this is because we got two different sets of, we got counters and we got the readout transistors. We got two layers of these, right? So that is, so we got some stuff going on there. And if I then go slower, and then I will have one more digit, then I sometimes need a little bit more time to make it good and stable. So there's some interesting things going on. And I know this digit here is having a problem with counting. So sometimes it's doing 3, or sometimes it's doing 4 or 5, as you see here. And then it adds some sort of crazy things. And I believe it's just because some of the neon bulbs here is quite dirty or something like that. Because it's there's both a count thing, but there's also a readout decoder. I should probably show you all this in a little bit later clip. But first I want to show you what I did to fix the input. So down here at the bottom, closest to the input connector, we got the input amplifier board. And it looks a little bit like this. And this was the one with a completely broken potentiometer. And this is the one you trim to find the correct drive for the output, the digital part of it. So first, this is your input, and then it goes via all those amplifiers, and they just amplifies and saturates all the way. So that means if you have a very weak signal, you will have a sine wave, and you will have a more powerful sine wave, you will have a clipped sine wave, then you have a square wave. I mean, that is just, and the more and more input you have, then you will have a square wave longer and longer down. That's just how it is. So that signal from this system here goes via a capacitor, and that is the one that was broken into the next stage. And that is the one with the variable bias. So you find the super critical, nice point where it's most sensitive. And this is where I've put it right here. And then there's the output transistor here. And because this one can do 5 megahertz, but the output is 30 volts. It's a negative 30 volts that goes out of this board. They have these power transistors in series to the negative 30 volt rail, and obviously they run them at quite high bias to make the system run fast. See, not that many signals goes in or out, but that is just a super little simple amplifier board. And that is what caused our missing input. And the reason why I figured this out, again, I don't have any schematics or service manuals or anything, but there's a test point and there's a trimmer. So obviously here you have to test for the signal, and there was no signal. And then I just measured, here's my input. This is connected directly to my input. Okie dokie, where are we? Along the transistors here, it gets more and more and more, and here we have nothing. Okay, easy peasy, where is it? And then just measure a little bit around the circuit. I actually wasted a little bit of time because I was stupid. Just pull out the two transistors and measure these first, because I mean, in 99% of the cases with this kind of stuff, it's just those burned transistors because they run on high bias, so they run warm, and obviously they will just break. But here it was the capacitor closest to the warm area that will have the shortest lifetime as well. That is how it is with capacitors and temperature. So now we can put this in again and see a little bit more. I'm still poking around with the frequency problem. So now I'm still here in frequency mode, and I'm running on the fastest gate time. So you can see it's just going really, really fast. We got quite a nice update speed. So this is 100 kilohertz. This is 110, 120. Fantastic. Let's just go to the hundreds. So this is 200, 300, and then it goes a little bit unstable. 400, oops, nothing. 5, 6, 700. Are we having fun tonight? Oh yes, I really want you to see something that is a little bit out of this world. So right now it's not counting anything because the sensitivity is cranked all the way down. So that means the input amplifier level is too low for anything to happen. All right, my input here is the green 10 kilohertz. All right, that tiny little spike you see here, that is the reset refresh pulse for the counter. All right, so now I will try and dial up the sensitivity knob just a little bit. Here you go. Now it's counting the 10 kilohertz. And what is now happening? It is somehow locking the refresh and reset and all that kind of stuff to the incoming signal. Is this just by coincidence, or is this random, or whatever it is? See, look at this frequency we have here. This is the frequency of the refresh, 3.4 hertz. So this is the fastest. So if I dial it a little bit slower, see, 2 point something. Let's just go a little bit slower so you can see what's going on. So now it's slower than 2 hertz. Of course, it's not measuring this here on this scope readout here because it's taking too long, but you can still see the refreshes and you can still see it is in sync with that. Okay, so let's just go fast as possible again. Let's try something else. So what if I take my 10 kilohertz and let's make this 11 kilohertz. Oh, see? 11, 12, 13, 14. So this is something it is doing for a purpose. That is absolutely crazy. And here we got all those 5 boards here. There is room for number 6, but it is not put in my unit. So we got 5 counters, and they are all divided by 10 with this kind of a keep out or a reset pulse. So this is the reset pulse we have. And the first counter takes the 100 kilohertz from the crystal oscillator board and makes it into a 10 kilohertz constant, fixed 10 kilohertz. All right, and then the next one, of course, this is the input, and here's the output. So the output is now reset pulsed with the display refresh little pulse. So let me show you something really funny. If I take the other probe and move it to the 100 kilohertz output of the 100 kilohertz. So that means this is 10 kilohertz, right? So here's my 10 kilohertz from the first 10 divider, and it is of course completely 3 running. No big surprise here. There's no reset pulses and stuff like that for this one. Okay, so the output of the next one, see, this one is the one with the funky pulse, right? So that is the output down here from that first, again divide by 10, but with this little pulse keep out thingy. And look at that. So there is this transient here that is now in sync with that one. But the others, they of course jump a little bit like that. Let me zoom out a little bit so you can see what is going on. So it's just modulated around that, but the average is the correct frequency, but it is kind of synced to that one, right? So let's move it one more step. So what happens if we go one more down? The more stable it gets and the more locked to the input it gets. Haba, interesting, huh? I think it is absolutely funny. And also, if we just have a little look at this, what happens if I now turn off the input? See? This still looks a little bit like that. And then, pink, it just goes to lock with that one. And I can, of course, remove the input synchronization. And then the input here will now be free running. So why the heck is it doing this? And I think it has something to do with, let me give it a little bit here. So we are now at 15 kilohertz. But I am now in divide by 10, right? So 15 kilohertz, and I have another 0 out here, right? So of course you don't want this first digit to go jump. So everything is locked to prevent that, to make it as nice and stable as it is. Aren't you a little bit impressed? So I think I'm done playing with this unit for now, at least. I still have a little bit of problems with their center digits. Sometimes jumps from 3 to 5. But I think it has something to do with the neon bulb resistor network decoder. So it goes from a binary coded decimal to the 10 digits for the Nixies, and that is of course inside this unit. But I already made this video way too long to repeat all this again, because I've already released videos that explains all the internal fancy things about those Nixie drivers and the counters and all that kind of stuff. So if you want to see how that works and you are missing this in this video, then please go to my video section and you'll easy find it. All right, thank you very much for watching. I hope to see you soon again. Bye.